Okay, everybody, we're going to start with our next talk now. So is Android Linux is next presentation brought to you by Dobrica Pavlinusic. Enjoy.
Thank you. And you haven't even heard anything yet. Hello, my name is Dobrica Pavlinusic, as he already said, and in this talk I will try to talk to you about my 10-year journey to have mainline Linux, you know, the one which I compiled on my own computer, running on the Android devices. Why we are talking about that today? Because in my opinion, with my GNU hat on, if you can't compile the kernel for your device, it's not actually Linux, right? If you can't download the Linux kernel and compile it and flash your device, that device surely isn't Linux. On the other hand, I don't particularly like Android, and I would rather run GNU userland on top of my device. How many of you actually have Android device? Almost everything. How many of you can actually compile the kernel for your device? Any device? Okay, few hands, much better than none, but in perfect circumstances, we all would raise our hands and say we have totally, completely free system. During the presentation, on upper right, you will see the year. If there is a year there, the statements on the slide reflect that year. So we'll start with today, 2019, and why we are talking about this topic today. Because nowadays, as we will see in the rest of the presentation, we are in much better shape than 10 years ago to be actually able to compile our own kernel. Most of the GPUs nowadays have reverse engineered drivers, which is somewhat important if you have a device which mostly has only the screen, so you probably won't run the headless server on your Android cell phone. But thanks to Linaro and Butlin and their efforts in the last 5 years or so, this is almost as possible as it was to install the Linux on your PC back in 1995. Which is actually a good place to be. In 2010, I got my first Linux device, which was G1, HTC G1, if somebody remembers, and I promptly bricked it, trying to get the root on it. At the same time, I started first of my Android-related projects, which is basically just a repository for useful command line utilities, which you can use to get some information from your Android device. It mostly uses ADB, and most of those things are actually somewhere on the web, but this is just a nice place to collect them all. On the other hand, I was very, very unimpressed with the Android ecosystem at all, because in 2007, so 3 years earlier, I actually had an OpenMoko, which was completely free platform for which I could actually compile my own kernel in my own user space, and I didn't have to first find a suitable security bug to be able to actually compile at that time Cyanogen for my cell phone, which is community supported. So not impressed. By 2012, if you remember, we had the TV dongle craze. It was the time where every device which wasn't a cell phone and had an Android had to have the HDMI connector only. And I decided to buy my second Android device for play. I decided to buy this Rockchip, which seemed like a good choice at the time because it was the dual-core CPU and costed $42. As you can see, my threshold for devices which I don't really need is kind of $50. And that device was my first attempt to actually run my own kernel on it. At that point, it was not supported at all. Even there was not even vendor kernel which I could compile and make somehow usable. But I learned that Rockchip, and we'll see that's mostly true for all the other manufacturers also, does have support which enables you to reflash device using USB only. You might ask the question, why would Rockchip do something like this? Because when they produced the dongles in the Chinese factory, the dongle, they actually solder all the components on the board, but the board itself is empty. The NAND chip on the board doesn't have the operating system, so they do need some kind of a mechanism to do the initial load. And we can use the same mechanism to actually take over the control of the device. Back in those days, Rockchip was just announcing quad-core CPUs, and they said they will use PowerVR, which is not well supported even today under Linux, actually not supported at all. So in a sense, I lost a little bit of interest for this particular board, although this board nowadays is actually supported by the upstream kernel. So if you have something like this, you can check out the kernel from gitkernel.org, and everything on this board will actually work. For other Rockchips these days, the support is also quite good, mostly because the Google at one point in time started to produce Chromebooks or Chromebooks with Rockchip chipsets appeared on the market, and when Google does that, a lot of things end up in upstream, so situation with Rockchip these days is rather good. A little bit later that year, I got another really cheap device. This was the Nook Color, which was basically designed to be very cheap Barnes & Noble's ebook reader. And this one also had PowerVR, which was somewhat unfortunate, but had a different CPU, which was OMAP. And I was looking at it and said, oh, it's a really lousy laptop. I'm wondering if I can actually make it somewhat useful for me. For example, to have secondary display with X11. And at that point, I learned that you can actually stop the whole Android user space, which runs on your phone, using those simple commands, and run your own binaries in chroot, for example, Debian. So this is one of the ways you can reuse your old device without flashing kernel. And then in 2013, I acquired my first all-winner device. I should say here I am all-winner biased. I like all-winner very much, and if you take a look at the years, I'm still using this device today, and it's really, really well supported. At that time, all-winner had either single-core or double-core CPUs. The CPU itself is designed in such a way that it will boot from the SD card if the SD card is present and has the correct magic values and bootloader on it. So it's also unbreakable. You can do anything with it. It also has the ability to boot from the USB. It's called FAL in all-winner. And it had really good community around Linux Sungsi, which actually did a lot of effort to mainstream all the things for all-winner. There is also the distribution called Armbian, which I can't recommend enough if your goals are somewhat aligned with mine. So if you want to run normal Linux, in this case Debian or Ubuntu, Linux distribution on your Android devices, take a look at Armbian. It has the huge support and a very knowledgeable community, and I would highly recommend it. On the bottom, you can actually see the graph of the GPU support. One of the things back in 2013 which I liked is that there is a start of the GPU driver, and it seemed to me that every day now we'll have the free GPU. As you can see on the graph, actually that every day now was several months before, so I was somewhat over-optimistic, but nowadays we actually do have the open source Mali driver, which actually works. Since this board was created before the Raspberry Pi 40-pin connector craze, it has a lot of pins, but unfortunately they are all in 2mm pin pitch. So another project which I found incredibly useful, it was the script which enabled me to print out the paper templates in perfect 2.54 millimeters pin pitch, just like the connector on this breakout board, which converts 2 millimeter to 254. And I found it very, very useful. So useful that I said, it's really lousy that it just generates SVG, which I can print. I can also use it to display the pins on the console. And not only that, it can actually look in syskernel debug and extract all kind of settings of your kernel. So it will display if you have enabled I2C or if you have enabled SPI. And if you have serial port, you will both see the designation of the serial port from the point of the CPU itself and from the Linux kernel. So in this example, UART0 is the CPU name for the serial port, and TTY-S0 is the kernel name for the same serial port. It also has the ability to flip the pinout either horizontally or vertically, which is rather useful if you are plugging your pins from above and then you turn the board on the other side to check something with the multimeter. It's useful, so you can say the script, okay, I flipped the board horizontally, and it will display the pins in the same orientation as the board you are looking at. Then, few months later, year passed by, and I decided to go all in and break my rule of $50 for the device which I don't need, and buy another TV dongle, which was, again, somewhat questionable choice. TV dongles are wrong form factor if you want to hack something or want pins, but okay. This one was IMX6, which was the darling of the open source community at the time, mostly because it did have functional GPU driver for its Vivanti GPU, which also took another few years to get in the mainline, but nowadays it is actually in the mainline. It had a community back then, it doesn't have it anymore. But if you are interested in IMX in any way, I can tell you that the Novena project, which was open source laptop from Bonnie Huang from several years ago, have last 50 units for just $200 at crowd supply, so it might be a good moment to snatch one. Then in 2017, I got another interesting device, which you wouldn't believe actually wasn't the Android. It was a Samsung ARM Chromebook, which was bricked to the point that the Google recovery mechanism didn't work. So what did I do? I tried to compile the Chrome. It didn't all go so well. Chrome, again, isn't Debian, so So I said, okay, this is the device. It has the flash in it. I should be able to reflash it. And I really was able to reflash it. That's the first time I actually learned that it's really good to pick up device which is supported by Google, because you can find a lot of upstream documentation from Google itself about the device if it's in one of the either ARM Chromebooks or some other device which Google supports. On this slide, since I'm using Chinese SPI flash, I have to warn you that this flash adapter actually isn't 3.3 volts, it's actually 4.9 volts, and it will work with 3.3 volts flash, but if you really want to be it on 3.3 volts, just look at this link. It's a simple matter of lifting one pin and connecting the wire to correct place. And the Chromebooks are interesting because they are actually designed so you can reflash it. When you open the Chromebook, it usually these days have the conductive sticker on one of the pads. This is the pad denoted on this slide with the yellow circle, which enables you to actually disable write protect on an SPI flash. So Google is actually giving you all the ability to take control of your Chromebooks. And in my case, I decided to take it. The problem was, and we'll come to this reoccurring problem, that if you want to do something like that, it's really good to have the serial port. The fortunate thing was that there was a schematic of the board itself, so I knew where the serial ports were, but one of them was 3.3 volt, and it was the STM32 microcontroller, which Chrome OS uses like a BIOS chip in a sense. It scans the keyboard and does power management. But the serial port which I needed was actually application serial port, and since this is the 1.8 volt CPU, it had 1.8 volt serial port. What can I do? Well, I can use my old Kindle, which also has 1.8 volt serial port to get output. Problem solved. So did it work? Well, back then, kind of. I was able to compile everything, but the U-boot at that time didn't support the onboard eMMC. U-boot just didn't see it, so I couldn't actually boot from the device itself. So I did a little. The funny thing is that I was able to flash the U-boot on the eMMC itself, and the laptop booted that U-boot from the eMMC, but once it started the U-boot didn't see the eMMC anymore. So I actually worked around and plugged in the USB Ethernet dongle and boot the kernel from the Ethernet, and then the kernel found the eMMC without a problem, and I had the distribution. The thing is, the display on this machine is so lousy that you actually don't want to use it as a display. But this actually gave me wings and said, maybe I'm not so crazy for wishing to run my own kernel on ARM devices. So, move a few years more, and in 2018 I acquired quite a few Tegra tablets, which are actually ThinkPad tablets, for which you probably never heard. I didn't either before I got those, which are basically also nice dual-core machines with gigabyte RAM and stuff like that. But at this point, I also had 2636 kernel from Lenovo, which actually released it because of the GPL obligations. I had a PDF schematic of the board, and the mainline kernel had already support for the Tegra chipsets, and there was third-party GPU support. So in a sense, it's almost like I was tasked with doing a board bring-up for completely new board. If you had a project like that, you would probably get stuff like that. You would get the board, the schematic, and some kind of reference implementation which somewhat matches your device. Note about the Tegra, if you look at those two graphs on the bottom, you will notice that Tegra is unfortunately still not part of the mainline kernel, but there is fork on GitHub which works. So I started looking for serial connectors. I spent some time searching through the board, through all 4-pin connectors, because I knew that serial was on 4 pins, judging from the schematic. And finally, I found it under the shield of the RF shield of the Tegra CPU itself. And again, it was 1.8 volts, but by this time, I already knew that there is a cheap USB serial adapters which have the iPhone keyword in AliExpress listings, which are actually 1.8 volts. So for this one, I didn't use the Kindle. Tegra, again, like every other ARM CPU, has some way to actually boot from the USB itself. On Tegra, it's called APX. Unfortunately, Tegra also does have some kind of crypto mechanism in the CPU itself. So this APX mod can be disabled by the manufacturer. I was happy enough that it wasn't disabled. And there are some projects in which people managed to break it. And I do have one Tegra laptop which is locked, so I do plan to test that. But in this case, I didn't need anything other than pressing one special key and powering on device to get the USB access to it, which enabled me to modify the flash at my will. So the U-boot was rather simple. I actually said, please compile me the U-boot. I used the reference platform on which this tablet was based, and I ported the minimum of the changes to see whether it works at all. And that was the display changes. And guess what? It worked. And now you will say, oh, you surely spend months porting those display changes. No, really, this is the amount of the code you actually have to edit to change the characteristics of your display. On the left side, you see the difference between upstream 2.6 kernel, which I have in Git, and the kernel provided by Lenovo. So Lenovo modified these lines to make this display works. And on the right side, you can see the current mainline kernel and the modifications I did. Really simple. Then I said, oh, this is very good. I have U-boot, now the kernel. So I got to the GitHub, compiled the kernel, again, did some minor changes like defining sensors, GPIO keys, and stuff like that. And in less than 400 lines, I actually had booting system. I thought that the next slide, this is the picture of the booting system, but it will come later. In this process, I learned a valuable lesson. If you are developing something from the ARM board and you will compile kernel multiple times, my suggestion is to actually set up NFS root. It will save you so much time, especially if you have multiple boards. For example, I used one board while the other was charging, and it was super simple to actually exchange it because all the data were on NFS server itself. Also, word of warning, for me, the U-boot would happily take the IP address for DNS mask over DHCP, but kernel wouldn't. So the command option IP DHCP, which should work in kernel, actually doesn't, but you can hard code the IP, and that's okay. On the other hand, the problem with this particular device is that the battery controller chip is actually not connected directly to the Tegra and under control of my software, but it has the dedicated 8051 chip with a kind of BIOS in it, which speaks with battery controller. So I wasn't able to actually charge the battery. After a lot of machinations and looking in the source code, I actually found the place in which they trigger the BIOS controller over I2C, and I was able to replicate that in the command line, which is this I2C set on the bottom, and I got my charging back. So in the end, I had a tablet from 2011 running X11, accelerated X11, and my favorite Debian distribution. So it really is possible. Of course, if you ever flashed your Android Mobitel, you know that when you download the distribution, it says this thing doesn't work, this doesn't work. And of course, it's not like everything works. For example, cameras are totally unsupported because there is no similar camera in current kernel, and the kernel is currently in transition between two camera APIs, so I didn't put much effort into it, but I probably will at some point. I'm not in the hurry. But other than that, it's actually quite usable. I will do some future works, but if you ever come to some Tegra device, this is the link with the notes which might help you. If you have some other device other than Allwinner or Rockchip or something, there is probably a community on the internet which you can turn to for initial help. I have here few links because I have few OMAP devices, so I somehow prefer it. But the two main stops for the beginning is either Armbian, from which you will get the latest mainline kernel which is supported, or the post-market OS, if you don't like Debian and want Alpine, which will enable you to actually run vendor kernel on your Android device, but with the current userland stack. So my suggestion is that those two projects are the first step to take a look whether your device is supported. So you may ask, okay, you did all that. Why did you do that? Did you get actually any benefit aside from spending a lot of time and compiling your own kernel? Yes, I learned a lot. But my goal, to be honest, was actually to be able to get USB OTG running under Linux. Not under Android, but under Linux. And it really is possible. Again, there is scattered documentation about internet. Here is the link to the GitHub repository in which there is a script which you can run on either all-winner device, on Raspberry Pi Zero, on QB board, basically on any ARM device with recent enough kernel, which is like 4 something or newer, to get either USB network card, human interface device, keyboard, mouse, and stuff like that, storage, serial. There is also webcams, printers, and stuff like that. So if you are security mindset, think USB rubber ducky, which you can script from the shell, or USB Armory, if you heard about that. You can do it yourself on any ARM board. You don't actually need to buy hardware. Word of warning, the initial motivation was to be able to use that USB emulated keyboard to emulate keyboard for the U-boot in the previously mentioned Tegra tablet, and that doesn't work, just so that you know. And this is the current state of that QB board you saw before. This is basically my bench power supply, which has 4 relay controlled outputs, has open source firmware on the step-down converter on the right below the multimeter, has the multimeter connected through the serial to this box, which enables me to control voltage, control and measure voltage and current I am feeding to my devices, which was very, very useful. So, and this is actually single core A10, so the device which you can actually borrow from some of your friends who are not using it. And this setup provided very, very useful to me, so hopefully it will motivate you to do something. And if all this is over the head and you said, oh no, I'm not really the kind of person who will compile the kernel, and you want still to use your old Android device for some new purpose, my suggestion is to take a look at Kotlin. It's interesting because it allows you to target old Android devices with the language which is much better than Java. It's so much better than somebody who never saw the language, like I didn't, and I actually never developed anything on Android. So I saw Java several times, and I can read Java, but I never developed anything reasonable in Java. But I was able in 2 afternoons to take almost perfect Kotlin application for my Android and modify it to be really, really perfect. And this is the beautiful use case for open source, which actually works, and for state of Android development in Kotlin, because for the last 5 years I was unable to compile most of the projects from GitHub for Android. This project was actually the NTP-controlled clock, which is basically Android with the Android application which has clock on it, because I ran out of batteries on the clock, on the real clock which is behind the cell phone. And in this project I learned that OLED displays really do have the burn-in. You know, when you have the same digits on the same place, it will change color after a while, like 3 months. When I put the white background, I can actually see the numbers, which are like light green because the reddish parts were burned out. And this was the reason I decided to change the software for something which can actually move the clock over the screen so I don't get the burnout. And another interesting tidbit, if you look at this picture, the back side of the phone is actually removed. That's because most of the Android phones are actually not designed to be always on, especially not designed to have screen always on. This cell phone, this is Galaxy Nexus, so original Google phone. This cell phone overheats if you don't remove the back cover and have the display turned always on. And this is AMOLED display, so it doesn't draw power other than for the pixels which are actually lit. Just word of warnings. This was the story from me. We passed few Android versions, and I hope you found some of this information useful, and I would be happy to answer any questions if you have them. Please raise your hand and we'll give you the mic. Thank you.